In this video, we're going to derive Newton's second law of motion, which is the famous equation F equals ma. This is one of the most fundamental equations in physics and forms the basis of classical mechanics. Newton originally stated his second law as follows. The rate of change of momentum of a body is proportional to the applied force and takes place in the direction of the force. But what does this actually mean in mathematical terms? First, we need to understand what momentum is. Momentum, which we represent with the letter P, is defined as the product of mass m and velocity v. So, P equals m times v. Momentum is what makes it hard to stop a moving object. For example, a heavy truck moving slowly can have the same momentum as a light car moving quickly. Now, Newton's second law states that the rate of change of momentum is proportional to the applied force. In mathematical terms, this is written as F equals dp dt, which means the force equals the derivative of momentum with respect to time. The derivative simply means the rate of change. So this equation is telling us that force equals the rate at which momentum changes. Let's expand this derivative. Since we have P equals mv, the derivative of P with respect to t is d over dt of mv. Using the product rule from calculus, this equals m times dv over dt plus v times dm over dt. Now, in classical Newtonian mechanics, we usually deal with objects that have a constant mass. When mass is constant, dm over dt equals 0, which means that term drops out. So, our equation simplifies to F equals m times dv over dt. We know that in physics, acceleration is defined as the rate of change of velocity with respect to time. So, equals dv over dt. We can visualize acceleration as the change in velocity over time. For example, an object that starts from rest and increases its speed is accelerating. So, substituting the definition of acceleration into our equation, we get F equals m times a, and there we have it, Newton's second law, F equals ma. This equation tells us that the force needed to accelerate an object is proportional to its mass and the acceleration we want to give it. For example, to give a heavy object the same acceleration as a lighter one, you need to apply more force. Or, if you apply the same force to objects of different masses, the lighter object will accelerate more. Newton's second law, F equals m, has countless applications in our daily lives. When you step on the accelerator in your car, the engine applies more force, which increases the acceleration, making the car speed up faster. Rockets use this principle too. They expel mass, fuel, at high velocity to create a force that accelerates the rocket upward. Understanding this fundamental relationship between force, mass, and acceleration helps us design everything from cars and rockets to simple machines and even sports equipment. Let's recap what we've learned. 1. Momentum is mass times velocity, P equals mv. 2. Newton's original second law states that force equals the rate of change of momentum, F equals dp dt. 3. For objects with constant mass, this expands to F equals m times dv dt. 4. Since acceleration is defined as A equals dv dt, we get the familiar form F equals ma. Thanks for watching. I hope this derivation has helped you better understand the physics behind one of the most important equations in science.